So are you able to see my screen?
Yes.
Online screen. Okay, nice. So everyone, so today's lecture we're discussing deep neural networks best practices. So these are the topics that we're going to cover today. So most of these topics are giving you guidelines, how you should, what action you can take to upgrade or improve your model. Okay. So we'll mainly discussing first. We discuss techniques when you have a neural network that is suffering from overfitting. What kind of action can you take to avoid that? And also some other recommendations on how you should design and implement your models. So the first thing that we're going to discuss is dropout. Before moving to dropout, we should first learn about bugging, right? So how many of you have heard about bugging before? Yeah, online? Can anyone briefly explain what is bugging? If you have heard about it before, go ahead, please. Mm-hmm. Yeah, excellent. So basically, bugging is a technique used for ensemble learning. Okay. So in bugging, you are given your data set. So as you can see here, you have your training data sets. Instead of training only one model, what we can do is that we can train different models. For that, we take the original input data, we perform something that we call bootstrapping. Okay. So this is sampling with replacement. So we randomly pick some samples to create n different subset of our original data sets. So with bootstrapping, you can have some samples that can be redundant on the subset that you have. Another thing is that each of these subsets should have the same size. Okay. So after sampling using bootstrapping, we have n different subsets. And on those n different subsets, what we're going to do is that we're going to train n different models. Okay. One model can be GNN, another model can be SVM, another model can be linear regression. Okay. So there is no constraint on what model you can train there. So you train all these models in parallel. And the assumption is that they are trained independently. Okay. The next step is to merge or combine all the prediction of these models. For example, if you are classifying digits, when you train your model, you provide one sample. This classifier can say, I believe this digit is a 1. Another can say, I believe this is 7. Another one can give a sum label. Or in this case, they give probabilities. Okay? So after doing that, we're going to combine all of the output of these classifiers to form one classifier that we call the ensemble classifier. Okay? And this classifier will just aggregate the outputs of each of the individual classifiers. Okay? So it takes what? The average of the prediction of those classifiers to provide the predictions. At the test time, when you provide the test data, we want each of the classifiers to give their probability of how they believe these samples, to which category these samples belongs to. Okay? So by doing that, we take the prediction of each of these classifiers and then we average them to have the final predictions. Okay? So this ensemble learning, we call this technique bugging. Okay? There's another technique that is boosting, where we are going from a weak classifier to a stronger classifier. I think that's the topic of the next lecture. So, but before understanding dropout, we need to understand what bugging is. Okay. So what can be the advantage of this classifier? The assumption that you can have here is that if you train this classifier on a subset of this data set, this classifier will have high variance, right? So each of these individual classifiers may have high variance because first, they do not observe the entire data set. They just observe a small subset. all of them will have a different idea of how the decision boundary is. All of them will have a different decision boundary, okay? So they have different models. And by combining them, if we combine weak classifiers or classifiers with high variance, the final classifier will produce less variance, okay? How is it the case? So let's discuss that next. So if you assume that each of the classifiers they produce this probability, okay, that is a random variable. And all of them, they have a variance sigma, okay, sigma square. So what will be the variance of their mean? So if we compute the variance of their mean, we take the variance of the average of the predictions. From the variance properties, this factor can go out and becomes n over n squared, 1 over n squared, variance of the sum. So again, from the properties of the variance of the sum, okay, is equal to the sum of the variances. So that's why we got 1 over n squared, sum of the variance on each output of the classifiers. As we said, each classifier is independent and identically distributed, okay, with a variance sigma squared. So we can replace this by their variance here. And then we make the computation, you have n squared, sigma squared divided by n. So the final classifier has n times less variance than all the individual classifiers. Does that make sense? So that's how your final classifier is having less variance than the original classifiers. So the integral classifiers can overfit, but the combination of all the classifiers may overcome the overfitting. Does that make sense? Good. So now coming to dropout. So in dropout, what we aim is that we want to leverage bugging in neural networks. Okay. So if you train your model and your model is overfitting, what action can you take to mitigate that overfitting? We saw before that bugging is a good technique for reducing the variance of a model. Okay. So how can we leverage this with in neural networks? So in dropout, what we do is that we basically remove nodes from the neural networks randomly. So with the probability P, we're gonna knock out some neurons. So we're gonna turn some neuron off, okay, by just multiplying, for example, their predictions to 0 or setting them to 0, such that the flow, when you perform the forward pass, this neuron will not influence the neurons in the next layers. Okay. So the idea is that if you turn off one neuron, you're having basically a different model. Okay. So by doing it randomly, we can therefore have a lot of sub-networks that are derived from the original original network. For example, one run of bugging can be, in this case, where you have these two neurons that were dropped out, okay? So when you perform the forward pass, with a certain probability, you turn off certain neurons. You can end up having this network, and the connections to this neuron will not be influencing the overall network. So now what do we have? We have one network. Before we had 3 hidden units in in each hidden layer. Now we have 2 hidden units in each hidden layers. And this is a different subnetwork, okay? And by doing so, you can then form a lot of subnets like this. So dropout can, in another setting, turn on these other 2 neurons, and then you have a completely different model. Does that make sense? So by randomly knocking out certain neurons, you're gonna have an ensemble of sub-neural networks. And these sub-neural networks are gonna learn something from the data, okay? And they can be high variance as we saw before. But how do we combine them? So by combining them, that's where we get the advantage of reducing the variance. So let's look at what happened next. So we saw that we can randomly turn off each neuron with the probability P. This is done in each forward pass. So when you're in your training loop for each batch, what you do is that you can sample a mask, okay? This mask can be a binary mask that indicates whether one unit is turned off or on, okay? And with this mask, when you forward pass, you can multiply the output of one layer by the mask, by the value of this neuron. Okay, so if one neuron was set to 0, this unit will not influence the output anymore. And we can have an exponentially growing numbers of neurons like this, or subnets like this. Okay, so if this number of subnets is exponentially growing, okay, can we train these models independently, individually? So you remember what we said about bagging. We said in bagging, each classifier is trained independently, okay, in parallel. So if you have this exponentially growing number of subnets, can we train them independently? Yes? Exactly. So generally this because you will have a lot of subnets. You don't have enough resource or enough time to train all these models individually, okay? But however, what will happen is that in Dropout, we can leverage something. Let's see what we are leveraging. So here we said that we train these models individually, independently, okay? But here, if we take these small networks, these are all the possible subnets that we can build from this one, okay? So what you notice is that there are some subnets that still shares some neurons, okay? So the assumption that they are trained independently is not exactly true here, because when I update this subnet, it influences the weight of H1. The same happened when I update this subnet share, okay? They are different subnets, but they share weight, okay? So this weight sharing is something that we're gonna leverage to be able to compute all the subnets independently, but we are not gonna compute all of them because this average is intractable, okay? Here what we have P of mu. Mu is the mask that generates one individual subnet. So your mask is a binary mask where you have 0, 1, whether a neuron is turned off or not. So this is exponentially growing. We cannot compute this. But what we can do is that we can estimate it, okay? And it is shown that if you sample only 20 to 10 masks like this and average their output, this is a good estimation of this average of the individual neurons, okay? So instead of computing all of them individually, we can just have few of them are enough to be a good estimator of the entire average of the networks, okay? So during the training, we're gonna just do what? Just average the output of reaching each forward pass. And that is a good approximator of the final model that we do, okay? So why does this work as a regularizer? So we said that in each forward pass, we randomly drop a neuron with the probability P. This will enforce each unit to not rely on any of the inputs, okay? So one unit will not, for example, this unit cannot rely on any of the input because they can sometimes be there, they can sometimes be not used to compute this unit, okay? So for example, if we don't knock out these two neurons, if all of them are used, we're gonna have this output, okay? But if Dropout drops these two neurons, we're gonna have this model, okay? Therefore, the activation of these units cannot rely on any of the inputs. And then the value of the weights are gonna spread out. So they're gonna shrink. And if you estimate the L2 norm of this one, you see that this is similar to L2 regularizer, okay? It can be shown that this is similar to L2 regularizer. So that's how Dropout can improve the generalization of the model or act as a regularizer. If you check the previous picture, you saw that there are some subnets that do not have any connections from the input layer to the final layers, right? So this means that basically we cannot consider this particular model in our input. But what we do is that it's important to choose the probability of dropping out the neuron such that most likely you will always have a connection from the input to the output layers, okay? how this is done, it is basically you can compute the probability, the expected number of neurons that remains after dropout in a layer. Okay, so how can we compute that? So what is the expected number of units remaining after applying dropout on this layer? Okay, so if the probability is P, you compute the estimated number of neurons remaining if you consider it as a random variable. Okay, you can show that the number of neurons remaining will be equal to NP. Okay, where P is the probability of retaining a neuron. So if our probability P is 0.5, we are sure that at least half of the neurons will remain after dropout on the expectation. Okay, so this is how we make sure that our layers will still have at least one neuron that will enable the model to forward and back propagate. Does that make sense? Good. So what are the notes that the takeaway that you can have from Dropout is that first, it's a type of regularization of neural networks that help to reduce the overfitting. So this is usually done when you have very large models, okay, and that are trained on a small amount of data. Okay. So usually Dropout uses probability 0.5, but it's recommended to choose a value between 0.2 and 0.5. Why? Because we said that we should at least make sure that we have some neuron that remains when we apply Dropout. Okay. We can also apply, that's a question for you. Can you apply Dropout on the input layer? Yes, let me ask online students. So Alexander Lovanov, are you there?
Yes, can you please repeat the question?
Yes, so the question is, can you apply Dropout on the input layer? So let's say this is your model. Can you apply Dropout here on this input layer?
I think no, because we don't predict something on the input layer.
Come again,
So
because?
I mean, because we don't predict anything on the input layer, so we don't have any classifier that exists in input. So I think it's not possible to.
Yeah, you remember when we were doing linear regression, what we had that sometimes we are not sure whether one input feature is important or no, right? So we can use L1 regularizer to set the weight of those features to 0, right?
Right.
So here it's similar. So we can assume that we have a subnet where we just remove one input unit, okay, to see how we enhance the network. So we can indeed apply Dropout there, but as you said, it's important to make sure that all the features are used. Therefore, you should have a high probability of maintaining one neuron in the input layer, okay? So we can use a different probability in different layers, but for the input layer, we can make sure that, for example, the probability that the input unit remains is 0.8, for example, right? So you are setting a bigger probability of having the input layer remaining compared to the hidden layers, okay?
Okay, I see.
So take away, if you apply Dropout on the input units, on the input layer, make sure that you set the probability that the unit will remain high enough, like 0.8, okay? So another thing is that Dropout is applied only during the training, okay? So I want someone to tell why can't we apply Dropout at the test time? Yes, so that's a good answer. Thank you. So because it's a regularization techniques, we do not need to regularize during the testing time, okay? But what if you use Dropout? What will happen? Yes? You may get random results, okay? So yeah, you may get wrong result, very random outputs. So the last thing to note, this is for your notes, Dropout is commonly used after dense layers. So if you have a neural network with convolutional layers, in general, we apply Dropout only in the dense layer because we have a lot of connection there. And those are the layers that are more prone to overfitting. Okay, you can still do it in the convolutional layers, but make sure that you set the probability of dropping a neuron very low, because even in your convolutional layers, what you have is that you already have small dimensions. You just have your filter. Your weight is just the size of your filter. They are small enough. So if you want to turn some of them now, to drop some of them, make sure that the dropping probability is very low. Okay. Yeah. So the next topic we're going to discuss, or if we can just go ahead and see how you can apply dropout in your model. So if you go to the initial lab where we discuss neural networks. So take a look at the architecture that we defined in the initial lab. So what we had I think online student cannot see this one. So this the neural network was contained mainly dense layers, right? So where we're classifying digits. You remember the lab 7. So here we have 28 by 28. This is the size of the input image, and we have the first hidden layer has 256 units. The next hidden layer is 100 units, and finally the output layer is 10 units. Okay, because we're classifying 10 digits. So if you want to apply a dropout here, what we can do is that we can define the dropout layer, and then we take it from nn.dropout. And that's where we define the dropping probability. Okay, we said that we should take a value from 0.2 to 0.5. Okay, so in this case, we can set 0.2, for instance. Okay, so now in our forward pass, we need to apply dropout layers in between those layers. Okay, so what we can do is that this is the first forward pass. So this means after here we are in the next layer, the next hidden layer. Okay, so here we can take the input and then we apply dropout layer. So we call it self-dropout that we defined before. And then we provide this. So what will happen here is that a mask will be sampled to decide whether among the 256 units, which of them will be knocked out. Okay, so few of them will be knocked out for this forward pass. That makes sense? By just multiplying what, remember when you have the action, we multiply the weight of the previous layer by the inputs, okay? And then you can multiply this by this mask, it will set them to, some of them to 0 before forwarding pass. We can again apply dropout in the next layer if you want, so you can apply them here. And then dropout again. Something that you should know again is that you can define a different dropout probability for different layers. It's not mandatory to have the same values, okay? And this is another hyperparameter that you can tune. So when you design your model, you can try in different drop probabilities and you find the best one. Does that make sense? So, and then you train your model as before. So when do you apply this? It's when you train your model, you remember how to detect whether your model is overfitting. So you first, initially you train your model, you check the validation loss and the training loss, right? And then if you notice that the validation loss starts increasing, then your model is overfitting. The first action that you can think about is, for example, coming back to your network architecture and include some dropout layers, okay? And you see how this affects your training. And most of the time you will see that this use of dropout will solve the overfitting problem. However, you can notice also that you introduce some bias in your model, okay? So your accuracy on the training set will not be that good as before, as without dropout, but your model will generalize better on the test data. So what is the goal? The goal is not to be good on the data that we see, on the data that we know, but to try to generalize. So if you introduce some bias, but gain on generalization, that's a good thing to do, okay? So Yes. Can you model? This can happen, but less likely, because the training set is, these are unseen data, right? So your model did not see them before. So in general, you most likely have better performances on the training set because those are seen data. And the goal is to transfer this performance to the unseen data that are the validation. So that's why when you tune parameters, we are finding the best parameters for our training data, okay, that will work best on our validation data, okay, or testing data. Good. Online, do you have any questions? Okay, if there's no question, let's continue. So that was the first regularization technique that you know. You can read more about Dropout on this book if you want to see, for example, how the training loop is changed. Okay, there are very few changes there. First thing to change is that you have to sample your binary maps, right? So you sample a binary map where you have, for example, if you have n units, you sample randomly to have 1 or 0 in a vector. Okay, and then you're going to multiply this after the forward pass. You're going to multiply this by the output of the layer that you're considering. And again, when you update the gradients, you also need to apply the same mask on your gradient, okay, such that these neurons will not influence your output. So the next technique that we're going to discuss is batch normalizations, which is another important technique, sometimes used for regularization, but regularization is not the main purpose of batch normalization, okay? And we're going to see what is the main purpose is to speed up the training. Why is it that batch normalization helps to speed up the training? You remember or you recall about the impact of data normalization and data standardization, right? So on your logistic regression model or linear regression model, where we have this model, we have seen that if we have some features that are in a bigger range than some other features, the contour plot of your loss function can look like this, right? It's very, it's kind of ellipse, right? And if the center of this contour plot is your objective is the best value that you're looking for, okay? Your model can take what? More steps to reach that objective, okay? But when we apply feature scaling, the contour plots of your loss functions can look more like this, okay? More round like this. And if you check how long it takes for moving from one position to the center of this contour, it's taking way less time, okay? So data normalization or data standardizations are used to speed up the training, for instance. Now, when it comes to neural networks, I have this model, I normalize my input, okay? But am I sure that to compute the output of this unit, okay, the inputs are then normalized. In general, they are not normalized, right? So you can normalize your inputs, but in between layers, you have non-normalized inputs for the next layers, okay? So the idea is, if we can normalize or standardize the inputs of the hidden layers, can this speed up the training? That's where batch normalization comes in, okay? So how we can leverage these normalizations for having only input features and instead having them into the hidden layers. Another purpose of that is that when we apply gradient descent, we are simultaneously updating the weight of all of our model, of all the layers, okay? When we are updating the weights, we assume that by updating these weights, the others will remain fixed. But this is not the case because you can see this connection. There's this linear connection and non-linear activations there, right? So this means when you update one, if you update the layers of this input unit, it will influence the weights of the other units, okay? So this means that your model or your gradient cards tells you that this is the value for this layer, these are the values that will get me close to the target or close to the minimum. Okay. But after updating it, because the previous layers were updated as well, it has an impact to this hidden unit. Okay. So the idea is like you are charting something that is moving. So you make two moves, but have one move back, because this has happened. That by updating here, it has impact on the other that you assume fixed. So it's like your model is chasing a moving target, right? And this will definitely take more time for your model to reach to converge. Okay, so batch normalization, and this problem that I'm describing, that's a problem that is called internal covariance shift. Why? Because we train our model also batch per batch. Okay, and then one batch, each batch can have different variants or different means and different variants. Okay, so when you update one batch, your model can think that, okay, this batch is talking about this particular distribution. Okay, but when you take another batch, it's a slightly different distribution that is coming in. Okay, so for all of this reason, what you want is that we want first that internal layers should have the same mean, okay, and the same standard deviation as we did of our input data, right? So how can we standardize it? That's the purpose of batch normalization. So the solution here is that for each mini batch, what we do is that we standardize the hidden values before feeding to the next layer. So this means that we want all of them to have the same mean and the same standard deviation. Okay. So how we do that is that, therefore, if we can do that, we can apply batch norm on each hidden layers. Okay, to make sure that all of them will have the same mean and the same standard deviation. This will fix what? The first problem of internal covariance shift, and we also do what? Speed up your training. Okay, so how this is applied in practice? In practice, if you assume that this Z is our mini batch of activation layers, we can compute the mean of for this mini batch, right? We can also compute the standard deviation, right? After computing them, we can then normalize. Remember how you apply standardization. You subtract the means, you divide by the standard deviation. Okay. But here, what we add another epsilon. So this epsilon is just for stability of the computations. Because if you have this sigma, if it's 0 when you're performing your forward pass, right? You can have some miscalculation, right? So that's why we put some epsilon to make sure that our computation will be stable. Okay. So what does it mean? This means that before feeding to the next layer, we're going to use this Z ground that is normalized. Okay. But this assumes this enforces our layers to have the same mean and the same standard deviation. But here, we enforce the mean to be 0. So basically, we are enforcing our model or our hidden units to have a mean centered around 0. Okay. But the problem of that is that we are restricting the space that our network can learn with. We are enforcing our network to say, okay, always have mean 0, standard deviation center around 0. Okay, standard deviation 1, for example. But this reduces the expressiveness of our model, because if your model can learn more, why do you extend your model to have only mean 0? Okay, so what we want is that we can say to the model, like, let's all the layers have any mean and any standard deviation, okay, to allow the learning. So that's why we parameterize by using lambda and beta. So we take what we computed before. This should be Z prime share, or fix it. So what we computed before, we multiply by gamma, and then we add beta. So these two parameters, this lambda and beta, they are basically learnable parameters. Our model can learn that. When we say a parameter is learnable, this means that they are also updated with the gradient descent. Okay, so we're gonna update them by taking the current value, subtract the gradient we expect to those parameters. Okay, then update it. But if you take a look at this formula, it can sound strange that why do we normalize first to 0 and then we change? Okay, but here is just if you replace this beta by mu and you replace gamma by this one, you will see that they are critically the same value. Okay, but we are saying that this beta and gamma can be something else that the model will learn. So after applying batch norm, the layers can then have different means and different standard deviation, not just 0 and 1. Okay, so that's how this reparameterization helps to keep or to preserve the expressiveness of the model. So now at the test time, batch norms it's a bit different. Why? Because you remember during the computation share, we update the units with a given mean and a given standard deviation. Okay, but if at the test time you can just evaluate your model on one sample. Okay, but on one sample you cannot compute means and standard deviation. Doesn't make sense, right? So how it's adapted? So at the test time, what we can do is that during the training, we're gonna compute the average of all the means and the standard deviation that we have. We're gonna accumulate this average. Okay, sometimes we call it running average. So during the forward pass back propagation part, you have mean standard deviation that you keep updating on average. Okay, and those are the values that you're going to use at the testing time when you want to evaluate your model. So even if you provide a batch, you don't need to compute the mean and standard deviation of this batch. You can just use the mean and standard deviation that you computed during the training. Does that make sense? Yes. Why? No, we are not using batch now, but we are using you remember how we define our forward pass, right? We say we take the units and then we replace the mean, we normalize, okay? So we cannot just turn off that code, right? So why do we get this mean and standard deviation if your inputs are having only one sample, okay? But what we can do is that we accumulate those mean and standard deviations, we average them during the training, we save them, and at test time, what we do is that we use those values that we saved before, okay? And yeah. The same value we use in the training for. Yes. 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 But remember, it's not the same value. These values are updated by the model as well. So you are taking the gradient step to update the mean and the standard deviation that they run, right? So, and this is done on multiple steps. Why do we take the average and only use the average? Because at the testing time, you can have only one sample. How will you compute the mean and the average of the mean and the standard deviation of one sample? Yeah. Mm-hmm. Yes. The value will be the same for each of them. The value no, but they can be different value. Okay, but they will be standardized in between layers. Okay, so for each of these layers, we will have the saved means that you accumulated, the running average that you have during the training. Okay. Yeah. So about the notes that you can take from here is that batch norm has great effectiveness when it comes to stabilizing your training. So we said before, if your model is chasing a moving target, it will not be the case anymore, okay? Because you assume that all your data should have a certain mean and center standard deviation, okay? So there will not be this covariance shift between your batches, okay? And also, since the input of each hidden layer is normalized, this improves the training of that layer because the inputs are normalized, as we saw when we have only a normal linear regression. And therefore, it will reduce the number of inputs that you need to train your model. Okay? So batch norm is important when you're doing also hyperparameter trainings. Okay? You want to do it as fast as possible. So you use batch norm to speed up your training to estimate the best parameters. So in general, what is the order of the layers? So for convolutional neural networks, what you do is that you have the convolutional layer, and then the activation, and then back scaling, and then you have the batch normalization. Okay? There's a debate whether you should apply a batch normalization before the activation or after the activation. Okay? This can also be one hyperparameter for you, so you can try and see what works best, right? But in general, what you do is that you just apply batch normalization after the convolutional layer. This includes activation, back scaling, and then batch normalization. And when it comes to dense layers, you apply the linear layer, the activation, and then you have the batch normalization as well. Okay? And then you can have the dropout. Does that make sense? So designing your network architecture, you should think of this order of layers when you want to integrate batch norm. And then batch norm, as we said, also sometimes provides some regularization, but this is not the main purpose. Sometimes you can provide, sometimes you cannot. Okay, but the main purpose is to speed up the training. So let's see very first how we can apply this. So we're going to go to the lab 9, where we had convolutional layers. I think it's somewhere here. For keras, we discussed this in the lab, how to implement the keras. Well, this right away with anyway, so if you want to define batch norm, so here we can define self. So here you can have batch norm of, for example, your first layer. So here you can call inland dot batch norm 1D. So you use batch norm 2D when you're having batch normalization in between the convolutional layers because you have a filter. But when it's dense layer, you use batch norm 1D. Okay, and you specify the norm of input. So you want to apply batch norm right after the first, okay, after the first hidden layer. So you want to say we have here, it's 100 inputs. Okay. So this means that before doing the dropout here, you take X and then you do self dot. You call the batch norm that you need, and then you provide this. Okay. So that's when enforce the normalization on this not particular layer. And you can have them start on different layers. Okay. So in the labs, we discuss also how this is done for convolutional layers. Well, so let's get back to our presentation, and then the next thing I'm going to discuss is early stopping. So, well, regarding early stopping, so when we train our model, it happens that the overfitting can start at any time, okay? And sometimes we have the assumption that what if we, since our goal is to be good on the testing time, at testing time, right? We just come back to the time where our model was good enough during the entire time that we train our model, right? So if you take a look here, before this U shape, right? What we have is that we have on the fitting, okay? After the minimum of this loop, we have overfitting that starts occurring on the validation set, okay? So the main idea of early stopping is that what if after my model overfit, I came back to the point where I had the lowest or the best validation error, and I use those weights, okay? Even if this will have more bias, but at least I'm sure that this will have better generalization, okay? So that's the idea of early stopping. So when you're checking your loss on the validation set, while for the training set, it is decreasing steadily, okay, almost smoothly, on the validation set, it does some ups and downs, right? And if it overfits, it can have some U shape, okay? This is mostly the case when you have a network that has the capacity to overfit first, and it is trained on small data set, okay? So the validation set can have this U shape. Why the U shape? Because at a certain time, your neuron will start memorizing your inputs. Okay? So that's how it will overfit. In this case, Dropout just said that during the training, I need to remember every time what was the best validation loss that I got. Okay? And as soon as this validation loss that gets worse, okay, I can stop the training after some time that I waited, okay, after some time of patience. And then I can restore to the time where I had the best validation loss. So that's the main idea. So regarding the implementation, during the training, when you do first step, you copy the parameters that provides the best validation loss, okay? Every time that you find the validation loss that is smallest than the one that you had, you save your model parameters. And then stop the training when there is no improvement after some time. So you can say that after 5 epochs or 10 epochs, if my model doesn't get better than it was before, I just stop the training, okay? And then you return the parameters that you stored as the best parameters. So this is how you implement early stopping. And this indeed will realize your model, because you're basically going back to the time where your model was good at the testing time, okay? Where the weights were not strong enough on the training set, okay? So therefore, early stopping can also be used when you do not know how long should I train my model. Sometimes you're struggling like, how many epochs should I define, okay? So we can define a certain amount of epoch, but with early stopping, saying that certain time it should stop, okay? So this can be used also to train or to select the number of epochs if it's considered as hyperparameters, okay? And this is the commonly used form of regularization in deep neural networks. So basically, when you train your model, the naive way to start is to have early stopping inside, okay? Yeah. But this comes with some drop downs, is that when you define your early stopping, for example, patience 10, it can happen that your model is just getting worse, but after that, it will get better, right? So this you cannot know, right? So yeah, that's one drawback of early stopping. So I think we implement this in the lab. We're going to discuss how we implement early stopping during the lab. Now about learning rate scheduling. So if you remember, we had about the stochastic gradient descent. The choice of the learning rate is very important. If you choose a large value, your model can overshoot or miss the target, as you can see in the left. Okay, choosing a large value can miss the target, and your model can diverge. Okay, your model can sometimes even reach the target but go somewhere else, right? But when you choose a very small value, you're taking more steps to reach the target. So there's kind of trade-off there. So how can I move quickly to the target? So learning rate scheduling just tells you that start with a big learning rate, okay? And the more your model, the time goes, reduce this learning rate by a certain extent. That's the key idea, okay? So you can need to find a function that can map how to decrease the learning rate the more the epochs are going, okay? And then you can then have something like this where you have, before you have a large update, start with large updates at the beginning. We're going to make a big step, right? But after that, you start decreasing your updates. So you're going to make smaller updates. So this is also useful to speed up the training and then have better, you have like, you spend less time training your parameters because of the choice of the learning rate, okay? Yeah. Now the optimizers. So regarding optimizers, you remember we discussed also in the labs, we saw like there are multiple optimizers that can be used. So some of them are chosen and are recommended to be used because they have proven to work very well, okay? Why? Because if you have your weights, sometimes your weights may not need the exactly same amount of step to converge, right? So some weights may need more steps or bigger step, and some may need smaller step, okay? So there's a kind of variance in the value of your weights in the updates. So what the optimizers does is that they estimate the average on how these weights are moving out, are updated, right? So if we can estimate this average, we can then provide the right step to take for each weight, okay? Such that, for example, if you take a look here, this weight can take, if you update, it can go up there, down, so you have these undulations, okay? Because one is needed more step than the other, okay? So these optimizers will give you this better estimation of how this weight are moving on average during your training and give you the right step for each weight, how you should take the step, okay? And this is how you can take, you go more straight forward than having the oscillations. Does that make sense? So we can read more about these optimizers, but the recommendation is that when you train a model, the first optimizer that you can try is the Adam optimizer, okay? You can use Adam optimizer, see how it works. If it doesn't work well, we move to MS Prox, okay? But in general, Adam optimizer will be enough and it is widely used. We also have stochastic gradient descent with momentum. So the momentum here is that to estimate how the weights are moving on average during your training and to estimate the right step you should take for each weight during the training. Okay? So I have linked some videos there. Want to learn more about these optimizers? You can watch them later. I think also have a course on optimization, right? You have a course on optimization, right? You do not deal with it. So the other thing that we're going to discuss, at what time are we stopping? I forget. At what time should we stop? 10:50. 10:40. Okay. So the next thing I'm going to discuss is gradient clipping. So when you perform the forward pass, you compute your gradient. You use that gradient to update your weight, right? So sometimes this gradient can be too big, okay? Too big that your weight cannot contain them, okay? Cannot store the value because it's too big. That's the problem that we call the exploding gradient problem, okay? So we need to make sure that our gradient will not get that big, okay? So this is what we use the gradient clipping. In PyTorch, this can happen when you update your model and you see all your weights are set to none. So if this ever happened to you in PyTorch, if it is set to none, so notice that what is happening is the exploding gradient is too big. So I should think, first problem it can be because you do not normalize your input data. Okay, another problem can be because your gradients are getting too big. And for that, there's what we call gradient clipping, where we basically set a maximum threshold. Okay, to say if my gradient exceeds this value, clip that. Okay, clip to the maximum value. Okay, and there are two approaches of performing clipping. You have the norm clipping, where we use the norm of the gradient to evaluate it. So basically, you compute the norm of the gradient. If it exceeds C, you replace your gradient. Here, delta is your gradient. Okay, you replace your gradient by delta multiplied by C divided by the norm of delta. Here, C represents the maximum value, okay, that the gradient should not have. This is also easily implemented in PyTorch or Keras, where you can have norm clipping. The other type of clipping is the value clipping. So in value clipping, here instead of clipping the norm by checking the norm, here we check the value, just the value. Okay. So we specify the range, like minus C to C, to say, okay, if the weights are out of this range, just clip and let it in the border of that range. Okay. So this function clip can be easily implemented to make sure that the gradient is used. This gradient clipping is also very useful for other purposes. Okay. For example, it's also very useful for something that we call privacy in machine learning, like when it happens that your model saves information about the data that you are sending to your model. Okay. So if your model saves the data of the inputs, someone can then, even without having access to your training data, infer if someone was used in the training or not. Okay, so gradient clipping is important to make sure that some sample do not provide too much information in your training. Because if one sample gives too much gradient, your model will basically memorize this sample. So this means that if you test the model with that sample and without that sample, you have a different output, a huge different output. Okay, So this tells you that your model has saved some sensitive information about someone. So that's how someone can attack a model to get the private information of the people. So gradient creeping is also widely used there. To creep the gradient, make sure that no sample is providing too much information to your data. Okay. So that was just a parenthesis. So yes. Yeah, the delta K is the gradient. The value of the gradient, yes. Come again? I think clip operator, what it does is that it checks whether the gradient is in between this range. So if your gradient is out of the range minus CC, it takes it to the border, like to the maximum of the, okay? Yeah. So the last thing that we've done, no, not the last thing, the next thing is the data augmentation. And this picture is very important when you want to compare deep learning and so-called old machine learning. So by old machine learning here, we mean SVM, logistic regression, linear regression, and so on. Okay? So it has been shown that the more you get data, all those old machine learnings, they have a steady point. They don't get any more data. Okay? Why? Because their capacity, of course. But neural networks, you can stack as much neural layers as you want, increase the capacity, so you are always free to learn something. So basically saying that deep neural networks will eat the data. Okay? But the more data you add to your model, the more your model gets better. This is for the case of deep learning. Okay? But sometimes we do not have more data just because we cannot collect them. Okay? We cannot have more than what we have already. The idea of data augmentation is, can we leverage what we have to create some fake data to augment our data set with and see how this improves our model. Okay? So this has shown to work. If you can generate fake data and augment your data set with, you can improve the performance. Basically, you can regularize your model. Okay? One naive thing to do so is, for example, you take your input data and you take one sample, introduce some noise, and consider this is a new data. Okay? This noise that you're putting, you're doing what? You're introducing some bias. Okay? By doing some bias, your model will not exactly learn what is inside the data, but we learn something approximated. This is also another form of regularization. Okay? But when you are dealing with images, we have different transformations that we can make on images without, if it's not noise. But if you have one image, the same sample, if you flip horizontally, you can say this is another sample. Or you flip vertically, you say this is another sample. So we apply some transformation on input data. Regarding images, there are a lot of transformations that we can do. Okay? So you take your input data, apply those transformations, but the transformation should be carefully chosen. Okay? Apply some transformations and augment your data set. Okay? So another transformation is rotation. So you have this rotation some degrees, augment your data set with. Do some other rotation, augment your data set with. Something here can sound contradictory is that we said that convolutional layers are translation invariant, right? When we use convolution layers, they can score features even if they are hidden, right? Yeah, but interestingly, doing so also works even though convolution layers are able to be like translation invariant. If a feature is somewhere, the convolution can still detect them, okay? But just because this is a different picture, how it's disposed, okay, the model can also learn some different things. But the idea is that this is just introducing some noise, actually, okay, to your data. And this helps for regularization. But some transformations are very useful, okay, because the input is different. It's different than the other data, so it can be seen as a completely new data set that you have. So what other transformation you can have? Take your images, imagine different transformation that you can make on an image. This is a possible transformation to augment your data set. For example, random cropping. You take the image, you randomly crop some place of the image, and use that new input. Okay? if you apply random cropping on the cat, it can be just the face or the eyes of the cat. Okay? Random crop augment your data set. Another thing is whitening, so you can apply some whitening to your data. Okay? So this means that you're reducing the impact of pixels with value 1. So you're putting them a bit toward 0.5 or 0. Okay? You're changing the intensity of the pixels to send to your input. This is a new data. Because at the end of the day, your neural networks are just seeing pixels, values. Okay? They're not seeing something else, they're seeing pixels and values. So changing those pixels and values such that from our eyes as humans, we still see one picture, okay? But the network will see a different picture in terms of pixels or values, okay? So you also have centering the input to, at least enforce the input to have the mean 0, like standardizing your input. You can also apply some affine transformations. So you take one image, skews it in a way that it doesn't seem like the ordinary image. Okay, this is also important. This can also help. You can also randomly apply brightness on some places of the images. There are a lot of transformations that you can do. So what people do is that some people will just propose a new transformation that works better. And say, oh, this is my creation. This is something that I found. Okay. So also there, we can think of that. Regarding a homework assignment, as the professor said, think out of the box. All these, you can use them. You can also see it as a small competition. Try to achieve the best performance as you can by using all those things like in a wise way. So you are given a task, you have a data set, you have a certain amount of data to regularize your model or to improve your model. Just augment your data set with random transformations. Okay? In PyTorch and so on, it's easy to do. Okay, so if we're going to discuss that also in the labs. So very fast. So here, so remember when we learn or we train our model to import the data set, you have MNIST or CIFAR or your custom data set. To form your data set, you can give some transformation there. Okay, in this transformation, that's where you can apply some transformations. Okay, so here, for example, this transformation is normalization. You say normalize around this value. Okay, normalize data around this mean. You can also, for example, say, okay, transform. You have all these different transformations, okay? And you can use, for example, random cropping, okay? So you random cropping, and you specify what is the size of the cropping that you want, or you want some padding and so on. So that's why you can augment your data set by giving all those transformations that we saw before, okay? So this is going to be back to it also in the labs. Yeah, so the next and the last topic that we discuss is the pre-trained layers. So maybe it has happened to you when you train the model, and then the next day you want to use the same model, but you did not save the model, for example. You start the train from scratch, right? And this is taking too much time. So what you can do actually is that in your network, the layers are just variables with values. Okay, with values, you can save them. Maybe in the dictionary, you say, okay, for this layer, these are the weight, you save them somewhere. And when you load your model, you also load it with the weight that you saved before. Okay, and then when you continue training, you will not train from scratch, right? So that's what we call pre-trained layers. So those are the layers where the weight were already optimized before. Okay, and this leads to a variety of possibilities to improve all of this. And we have these pre-trained layers in two modes. We have the unfreeze mode, as I said before, is when you have your weights, you load them, they are pre-trained. This means you have optimized them before, okay? They are unfreeze. This means that you can keep updating them, okay? They are not frozen. So you pretend you load them and you keep training. Okay, let's say you started training your model yesterday, you trained it for 10 epochs. Today you load it, you continue for training for 10 or 100 more epochs. Okay, this is what we call the freeze mode. And then you have the freeze mode. Why it's more interesting is when your pretend layers, in your pretend layers, you don't update their weight. Okay, they're already pre-trained. However, you can use them as a kind of feature extractors. So you have your input, you pass them to your pretend layers before, using them for a different task or for the same task or for something else. Okay, and this leads to something that we call transfer learning. So you have a model that has learned something before. If it is convolutional layers, this means that it has learned some low-level features that can be put in together, can give some high-level features. Okay, so how can we leverage those low-level features that we learned before on a different task? Okay, so that's what we call transfer learning. You do not update those pretend layers, but you just update on the new task. So you use the pretend layer as a feature extractor, for instance. So what transfer learning is something that also works for us as human, as assumption, is that you have a task, you know how to ride a bicycle, okay? To learn how to ride a motorcycle, you can leverage the learning that you know from bicycle to motorcycle, right? Why? Because the assumption here is that the factors that help you to learn how to ride a bicycle are the same factors that can be useful to impact the training or the learning on to riding a motorcycle, right? So that's a core assumption. Can we use that for neural networks? Yes, we can actually use that, and it works pretty well. How? Is that you have a huge data set that is available publicly. Have a huge data set. Huge. This means you have hundreds of thousands of images, for example. Okay. Like training one can take 24 days, 24 hours. Okay. Training for one epoch or 3 epochs. It can take 3 days on your computer. So you cannot afford training this kind of data set on your computer, right? But there are some people that have a lot of resources. I mean, like a lot of resources that they can afford training such models. So they will take a big source data set, train them to classify a big range of categories. Some even have 1,000 categories. Okay? The small size of this is what we saw, maybe we discussed in the lab, is, for example, the CFA10 data set that classifies cat, dogs, automobiles, planes, and so on. Those are just 10 categories. Okay? There's some other models that we have thousands of categories. Okay? Yeah. So this means that the convolutional layers part has learned a lot of features, a lot of low-level features. Okay, that will be useful for you. So this means I have a new data set where I have a small samples, or I don't have enough samples. Okay. Instead of training my model from scratch on only this data set, I can load the pretend layers on the bigger data set, where I'm sure that the convolutional layers have discovered a lot of low-level features that are useful for my task. Okay, so there cannot be a disconnection between those tasks. There should be something related. But for images, it works. This assumption almost fits every time, because if you have a model that was trained on tons of thousands of images with a lot of categories, if you want to do a task on any image, most likely those low-level features are useful for the task as well, right? So in transfer learning, to design your model, let's say this is your architecture. This is the classifier, this is your architecture. Instead of just training this small part, that is the classifier here, what you do is that you take the pretend layers. There are a lot of them. Some of them are trained on a data set called ImageNet. Okay, you can have VGJ with different sizes. You have some models with deeper models or less deeper models, or and so on and so on. Okay, this will be also discussed in the lab. All those models are available, for example, in PyTorch or Keras, already trained. Already trained means their weights are saved. So you can download their weights, load them, and have this model ready for you. What you can do is that when you define your architecture, instead of just saying this is my architecture, you assume that you have some previous layers that are not your layers, but some other layers that are useful for you to transfer the learning from that domain or from that layer to your training. So what you do is that you take the, for example, the VGG, let's say 16 or network, this network, you disconnect the classification, the classifier part of that model. You disconnect this means you remove the layers. You attach them to your model, okay? And then what you do is that you freeze those models. Freeze a model means that you do not want the gradient to flow there, okay? And in PyTorch, for instance, you know there's this required gradient variable, which tells whether a parameter or a variable requires a gradient or not. So you basically set requires gradient to false for all of these layers that you get before, okay? And then you attach your head, the head. This head is your model. So you want to predict, let's say, you want to predict whether there is someone in this room, for example, okay? Or identify people that are in this room using a picture, okay? You have your labeled data set where they have crops, everybody, every single person in this room, okay? Here. So this will be, if it is just predicting yes or no, this is a binary classification. To have a very accurate model on here, it's quite difficult. You have to pre-process your data, you have to do some stuff. But you can, if you don't have enough data, you may not achieve more than that, right? So depending on how many targets you have on your target task, on the new task, you're going to define your own architecture, but you connect it with a pre-trained architecture, okay? And all of this, for your new training data, you pass them to the frozen part. All the features extraction that they know, the low-level feature that they know, they will all be presented to the input as your model for your model, okay? And then during your updates, you perform the forward pass everywhere here, but the backward pass to update the weight stops exactly here, okay? Complete the loss, back propagate, and so on and so on. So basically, you are specializing this head for your task. But the previous layer was specialized on a different task, okay? So this pretrained layer is very important, very useful when you want to train some different models. But sometimes it is in the semantic nature or the nature of the inputs that are shared between tasks. But it's actually the target. So you have a task that you need to define to, let's say you have a model. There is this interesting example where you want, for example, to you have a model. Let's say you have a model for different texts, okay? And you want, for example, these different texts to be to synthesize a sound from the text, okay? So you're giving a text, you want to generate a sound from the text, okay? But you have text that are from different languages in the labels. So you have the text, there are labels from different languages everywhere. So this text can be X1, X2, X3. They can have different size of the inputs. So they don't necessarily have the same size. And they can be trained on one model as independent models, right? So you have this, and that can text a test in French, generate the sound in French. Another one, but you can have some of them that are very similar, close to each other. For example, let's say have a text in English, but that is labeled with the English accent, okay? You have another text in English that is labeled but with American accent, right? So all of them can be trained by individual models, right? But what you want is that you want one global model to do the final job. So you have shared, instead you have one shared layer that will connect all the outputs of the individual task, okay, to produce your final output. So in this case, what you notice is that it is not the task that are sharing the input layer or the input domain, but they're sharing the output domain share, okay? So H1, H2, H3, those are those models or layers that can be used individually, but then you combine all of them, sure, okay? So to create this kind of architecture is pretty straightforward. That's why we use PyTorch, because here it gives you some leverage. You can do low-level things compared to Keras, for example, where you just compile and run. Okay. So yeah. So here, if you want to create this kind of architecture, you define the architecture of each of the single models. Okay. And then you define the shared layers. The input of the shared layers, the size should be the size of the output of all those kind of layers. And these layers, they can have different input sizes. Okay. So in your forward pass, you can then pass 3 variables for each task. Okay. You take these variables, you forward them to your individual models in your forward pass, and then you take the output of them, you put as the input of the shared layers, and so on. The backpropagation can also work here very nice. So you can read more about this in this book. Deep learning book. I really recommend you to read it. It's important if you want to know things in details. Also, if you're interested in doing some research and doing some other things, it's important to read that book as well. Yeah. So we are almost at the end. And as a summary, we saw that regularization techniques for deep neural networks, so that if your model, you want to regularize your model, you can use Dropout, you can use batch normalization. In Dropout, you randomly turn off some neurons, okay, to increase the bias of your model, but indeed increase the variance at the end, okay? For batch normalizations, you use it to speed up the training, stabilize your training, and also add some regularization at the end. Early stopping, sometimes your model starts overfitting, but you want to save the model that has provided the best performances on your validation set. So you get back to the parameters at that time. And for data augmentation, is that you apply some random transformations on your input data to augment your data set with. This has proven to improve the performance of the model, because deep neural networks seems to have no limits as much as you have data. Okay. And about optimizers, there are several optimizers that you can use. Some of them are just, if you know the normal stochastic gradient descent, so some of them are just estimating a way of finding the moving average of the width, okay, in order to update them to avoid some oscillation in during the optimization. This can, all of them help to speed up the training, and it works very well. And finally, we discuss Pretrained Layers, where you can save the weight of a model and use them later on to speed up either the training, you must start from scratch, okay, or to transfer learning from a previously trained model on a huge data set on your task, okay? So some of this topic will be covered in the lab. And now I would like to ask if you have any questions. The question, usually do you record the attendances for the lecture? No? Okay. So thank you, that's it for today. Have a nice day. You're welcome.